Howdy, students. So today we're going to talk about one-dimensional kinematics, specifically the part of mechanics dealing with the science of motion using words, diagrams, numbers, graphs, and equations. Kinematics is just part of mechanics. And really, we're trying to make mental models that can describe and explain real world things. Basically, how things move. So, we're going to talk about scalars and vectors, and they become really important in kinematics. Scalars are quantities that just have a magnitude or number. Vectors have a magnitude and a direction. So let's talk about some examples, and I'll have you figure out whether you think they are vectors or scalars. So 5 meters, 30 meters per second, east, 5 miles north, or 20 degrees Celsius. I want you to try that, figure out what you think each of them are, and then I'll tell you. So, because even though these all have units, some of them are going to be scalars. A does not have a direction, so it is a scalar. It's just a magnitude. B has a direction, 30 meters per second east. It's going to be a vector. C, 5 miles north, it is going to be a vector. And then D, 20 degrees Celsius, well, that's not 20 degrees Celsius up or 20 degrees Celsius down. That is also a scalar, the trickiest one of the bunch. But this doesn't need to just be a cardinal direction. It could be right, left, forwards, backwards, up, down. All of these would also be directions. If added to a number with a unit, would be a vector quantity. So let's talk about one scalar and one vector quantity. You may have talked about distance and displacements before, and how they seem to be very similar, and sometimes they are, but we're going to deal with many scenarios when they are not the same. Distance is just a scalar quantity that means how much an object has covered during its motion, whereas displacement refers to how much out of place the object is, or how far it has gone from the original location or position, I should say. And an object's overall change in position is called the displacement. And I want to say position is sometimes going to be abbreviated as x. So displacement is oftentimes delta x, or change in x. So I want you to try this, and then I'll go over the answers. We've got A, B, C, and D. And I want you to use the diagram to figure out what the resulting displacement and the distance traveled by the skier during these 3 minutes are. For this skier, between A and B, during that first minute, he went a long distance, 40 meters plus 100 meters plus 40 meters. And 1 minute he had covered 140 meters. Then he turned around and he went 40 meters plus 100 meters in the opposite direction. And then he turned around again and he went 100 meters to the right again to end up at D after 3 minutes. Now, if we're talking about his distance, we're talking 40 plus 100 plus 40, that's 180 meters, plus another 40 plus 100, that's 180, 220, 320, plus another 100 meters, 420 meters. That's his distance. However, if you look at his final location, reference to his original location over here at 0 minutes, he has only gone 40 plus 100 meters. That change in position overall is only 140 meters in the right direction, or the positive direction is oftentimes called. So not only will we talk about distance and displacement, but we're also going to talk about speed and velocity, which are also going to be scalars and vectors, respectively. So, speed, even though we might use these interchangeably, sometimes when we're only talking about positive velocities, speed is that scalar quantity that refers to how fast an object is moving. Speed can be thought of as the rate at which an object covers distance. Velocity is a vector quantity that refers to the rate at which an object changes its position. So we'll talk about the difference between those two. The direction of the velocity vector is simply the same as the direction of the object is moving. It would not matter whether the object is speeding up or slowing down. That's something that we're going to talk more about towards the end of this. And just talking about it, velocity is always going to have a direction. And oftentimes we use positives and negatives with velocities. We won't with speeds, but with velocities, we will have positive and negatives. And rightward is typically a positive, and upward is typically a positive, whereas leftward or backward or downward are going to be negative velocities. So the equations, if we wanted to figure out the average speed, that would be the distance traveled during the total time of travel. Whereas average velocity is the overall change in position over an amount of time, or the displacement in the amount of time. So there's also a difference between instantaneous speed and average speed. The instantaneous speed is the speed at any given instant in time. So I look down at the speedometer in my car. I am going, 35 miles an hour. Whereas an average speed is going to be the total amount of distance over the entire time. So, maybe I drove to Milwaukee, even though at one point I'm driving 75 miles per hour. I could figure out how much distance in total I had covered and divide by how much time, how many hours it took me to get there, and that would be my average speed. Note, in both of these scenarios, I didn't say 35 miles an hour north or 35 miles an hour south. That would make it a velocity and not just a speed. Let's also talk about acceleration. This is also a vector quantity because it relates to whether you have a positive or negative change in your velocity. Anytime a velocity is changing, that is an acceleration. If it's the same amount of change in the velocity per second, that is a constant acceleration since the velocity is changing constantly. An object with a constant acceleration should not be confused with an object with a constant velocity, though. A constant velocity means in the you set that cruise control, and you're going, 60 miles an hour. That it would be a constant velocity, whereas a constant acceleration would be, you're hitting the pedal at the same amount and you're increasing the same amount every second. Maybe it's 60 and then 62 and then 64 and then 65 miles per hour. And then 66 miles per hour. That would be an increase of 2 every time, meaning it would be a constant acceleration. With velocity, changing velocity over time, or v final minus v initial over time, that's going to be our average acceleration calculation as well. We can show motion in many ways. One of the best ways, and what we will utilize a lot, is a graph of the motion. And in this case, this is sometimes called a ticker tape diagram or just a dot diagram, where and I know there are cars here, not dots, but the way it works is it's going to, between each picture is going to be the same length of time. So you'll note it goes 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So this is 1 second is going to tick by every single time. And then in the bottom is going to be showing the position of the vehicle or dot or whatever object in any given amount of time. So you'll note in this first diagram, we see 10 meters between every single second. So 10, 20, 30. Whereas in the bottom, we see, again, same amount of time between each picture. But in the bottom, we see first a change of 2, then a change of 6 meters, then a change of 10 meters, then a change of 14, then a change of 18 meters. So note that these are not exactly the same. This was constant in its change, and this is a changing change in position. So we would graph the first one because it's changing the same amount of position in the same amount of time. This would be a constant velocity, and it's a positive velocity because it's increasing its change in position. It's changing in the positive direction. Whereas in this graph, this is more like the second scenario where in the first amount of time, it only changed a small position. And then the second amount of time, it only changed a little bit more. And then the third amount of time, it only changed a little bit more. And a little bit more. And then finally, that 18. So in any given amount of time, it increased its change in position. So it had a changing velocity or an acceleration. And with that, you may have noticed me moving up and over, a rise over a run. I was looking at the slope of these two graphs, or of those graphs, because that tells me what's happening in the velocity, how the position versus time is changing. In both scenarios here, we have a constant velocity because the slope is changing the same amount. However, we can see that this graph has a faster velocity than this graph because this graph is changing its position more in the same amount of time. It has a higher slope. So just talking about slope on a position time graph is the change in position over time, which is the velocity. Something we haven't talked about much yet is the slope on a velocity time graph is the change in position over time, which is the acceleration. So I want to challenge you a little bit. On your own paper, and I'll describe what the answer should look like, but on your own paper, I want you to try to draw a position time graph and a velocity time graph for this dot diagram here. So for this dot diagram, draw a position time graph, that's the x, and a velocity time graph in your own paper, and then I will show you how it should look. All right, so this is the graph that I drew. I graphed my time here, my positions over here. Remember, this is going to be, x is going to be the position. That's the letter we use. We don't use p because p is momentum, which we will get to later. But we see for each of the changes, we see a changing slope. Look at that slope. It starts very flat, gets a little less flat, a little less flat, a little less flat. And finally, it's a pretty steep slope, meaning we have a changing velocity. And if I graph the velocity, remember the change in position over time is going to be the average velocity. That's fine to graph if we do not have information about the instantaneous velocity. So in the first second, we had a change of 2 meters in 1 second. So that was the velocity. The second, we had a change of 6 meters in 1 second. So that was the velocity. And then we have 10. And then we have a change of 14. And then a change of 18 meters per second. And as you can see, the change in velocity in an amount of time is about 4 meters per second. So that was 4 meters per second that was the change in velocity in that amount of time, which is the acceleration. So on this graph, we see the slope change. So we see a change in velocity. In this graph, we see the same amount of change in velocity for any given amount of time. And thusly, we see an acceleration that is constant. So a constant slope on a velocity time graph means a constant acceleration. If we graph our velocity time here as well, we can see we have a positive velocity with 0 acceleration. That's your scenario where you set the cruise control at 60 miles per hour and don't hit the accelerator. You're not changing your velocity. Thusly, of 0 acceleration, we see a nice horizontal line. Whereas if you're hitting the accelerator, you're hitting the gas and you're hitting it at a constant rate, you would see the velocity change the same amount per second. So we see a positive velocity with a positive acceleration. This is where things get a little tricky, so I want you to pay very close attention. In both of these scenarios, we have a changing velocity. So we have an acceleration. In fact, it's a constant slope. So it is a constant acceleration. But in both scenarios, the velocity is positive. So if we are just moving left to right, say you were a runner moving left to right, in this scenario, they're moving rightward. In this scenario, they're also moving rightward, but they are decreasing their velocity. However, they are still moving in the positive direction, so they have a positive velocity. In this one, we see a negative velocity. So this is a moving backwards, or a moving downwards, or a moving to the left, if we have called to the right positive. In both of these scenarios, the velocity is negative. We see a negative velocity. However, they're doing different things. In this one, we see the velocity start moving very quickly backwards, and it's moving towards 0. So if your velocity is moving towards 0, your speed is decreasing. I'm bringing back that scalar again. Your speed is decreasing. You're moving towards 0. However, in this one, we started at 0, and then we started moving faster and faster in the backwards direction, because we have a 0 velocity, but the magnitude of the velocity is going up, so the speed is going up. So this is speeding up versus slowing down. In both of these scenarios, we see speeding up because the magnitude is going to get higher. In this case, we start at 3, maybe it's 3 meters per second, and we move towards 9. That's probably the easiest one to understand, speeding up. However, in this scenario, we are starting at negative 3 meters per second, and we're going to negative 9 meters per second. So even though you're moving In the negative direction, your speed is increasing. You're getting faster backwards. That'd be speeding up in the negative direction. This one, we are slowing down. We start with a positive 9 meters per second. We go to 3 meters per second. That makes sense that you're slowing down. But in this one, even though the slope is up, you start going negative 9. So you're moving backwards quickly, and then you move less quickly, less quickly, less quickly, less quickly, and you are slowing down. You're moving in the direction you were moving less fast, so you were slowing down. And here are the kinematic equations. This may seem like a lot, but it is not that much. I am going to, and you will get these equations on your equation sheet, which you'll be getting. Rather than having D, it's fine to use D, but I'd prefer you write in delta x here. You're going to see it both ways. That's why I've included it both ways. But I think we're going to stick with delta x. So anytime you see D, I'd like you to write delta x. Because these are really vector quantities, so we should really be writing in change in position or displacement instead of D, but you might see this D to stand for displacement sometimes. But this is the better way to write these. Delta x, delta x, delta x instead of the D. And delta x equals your initial velocity times time plus 1/2 times your acceleration times time squared. This is another equation. These are the 4 that we will use, and we will practice using these. We have final velocity squared equals the initial velocity squared plus 2 times the acceleration times delta x. We have the final velocity equals the initial velocity plus the acceleration times time. We have the delta x displacement equals the initial velocity plus the final velocity over 2 times time as well. Write down these equations. I don't expect you to know how to utilize them just yet. We're going to go over something called an equation picker chart, where we will figure out how to best use these equations, but I just wanted to expose them to you right now. These are going to help us make a mental model and solve some problems, right? So I hope that was helpful. It's a lot of information all at one time, but I truly believe you all will be masters with this in the very near future. All right. Hope that was helpful.